Welcome to another video. This problem is from 2015 Harvard MIT Mathematics Tournament. Now this question is easy, again, like all other problems we've done, when you know what to do. When you don't know what to do, it is impossible to solve. So let's read it together. It says, let R1, R2, R3, you keep going till you get to Rn, be the real roots of this polynomial equation. Evaluate the sum of the squares of the roots from R1 to Rn. Initially, I thought this is a very easy question because I can use Vieta's formula to calculate the sum of all the roots or the sum of their squares by doing some adjustments. But then I looked at this key word. The word is real. So it means you have to know how many real roots it has and what polynomial generates the real roots. So there's a lot of work involved in it. So the first thing I thought was there has to be a way to factor this into two different polynomials that multiply each other such that part or the whole of one of the polynomial will not have any real root and the other one will have all real roots. And I have to be able to show that the roots are real or not real before I can use Vieta's formula. So you can see that it's kind of hard. Well, that's why it's in a mathematics tournament, but we'll do it in this video. Let's get into the video. The very first mission is to factor this, and factoring it does not look easy. And because it's a competition problem, you're allowed to try and test stuff, okay? So what I'm going to do is, I know if I take these last three, I can factor it into anything reasonable. If I take the first three, 14 and 8 don't go, except 4 times 2, wait. No, but this one is a cube, so it doesn't make any sense. Okay. This 8 is easy to generate. So what I'm looking at is, it is easy to generate something using 8 than to generate something using 14. The way I'm thinking of it, rewrite this 14 as 16 and 2. And then I'm going to think of a way to rearrange it. So we have P of x. Let's just write it this way. P of x equals x to the 8th minus 14x to the 4th. If I rewrite this, let's see, this is x to the 8th minus 16x to the 4th plus 2x to the 4th. Okay? Minus 8x cubed minus x squared plus 1. So now I need to find a way. This is promising because it looks like 16 is going to go with 8. Wait. I think I found something. I think if I put these together, x to the 8th plus 2x to the 4th plus 1. Let's not put them in parentheses yet. See, I've taken this, this, and this. Let's see, minus 16x to the 4th minus 8x cubed minus x squared. What can I factor out? Oh, I can factor out x squared here. So here, this clearly is a perfect square. This is clearly x to the 4th plus 1 squared. Always look for things like this, okay? Minus, it's possible I'm going to get something on this side also, okay? What can I factor out? I can factor out, there's no 2 okay, I can take out x squared. And then I have 8x squared minus, no, it's not 8, it's 16. Come on, it's 16x squared minus 8x minus 1. Okay? Now what does this look like? Oh, again, this is x, this is x squared times 4x. No, this is plus. Ooh, I took out the minus, so this is going to be plus 1. I got it, squared. This is a perfect square again. So everything is squared. Nice. So this is going to be x to the 4th plus 1 minus this. So this is squared, this is squared. This is the difference of two squares. Okay, let's go on. So we have p of x is equal to, actually, instead of me squaring just this, I might as well put the x squared back, and instead of writing this, let's rewrite it here. So this is going to be x to the 4th plus 1 squared minus, I'm going to combine these squares, so I have, now this becomes 4x squared plus, this becomes x squared. Do you see that? So what I did was I took away this square, put it here, so everything was x times 4x plus 1, and then I pushed the x inside. So this is what I have. This is the difference of two squares. We can now be written as x to the 4th plus 1 plus 4x squared plus x times x to the 4th plus 1 minus 4x squared minus x. I distributed the negative when I did the second part of my difference of two squares. Now see, I have something nice. X to the 4th plus 4x squared plus x plus 1. Nice. And I have x to the 4th minus 4x squared minus x plus 1. That's it. That is the polynomial we had at the beginning. And this polynomial is equal to 0. So, and I already see something beautiful. Whenever you see a polynomial where all the terms, not all now, okay, at least I have 3 of the terms are positive. No, 3 of the terms are always positive. You see that? This is always positive. It doesn't matter what x is because it's raised to an even power. This is positive, positive, positive. 1 is positive. The only thing that can be negative is x. This can never cross the x-axis. It will always be floating up above the x-axis because it has no real roots. How do I know? Case 1. Let's even do greater than or equal to 0. If x is greater than or equal to 0, this polynomial, to take the case of equal to 0, this would be 0, 0, 0, but there will be 1 remaining, so it's going to be greater than 0. Therefore, it will not cross the x-axis. Remember, the roots of any polynomial or any polynomial equation is always the value of x when the polynomial crosses the x-axis. That's how we solve them graphically. So here, this will never cross the x-axis because it's always greater than 0. Now, that's when x is greater than or equal to 0. Case 2 is when x is less than 0, but it is, case 2, let's say negative 1 is less than x, and x is less than 0. So we're talking about very small number, okay? Or when we say the absolute value of x is less than 1. If the absolute value of x is less than 1 and x is negative, it means this is going to be positive, this is going to be positive, and a small negative number added to 1 is still going to be positive because the absolute value of the number is less than 1. So if you have negative 0.5 or 0.9 plus 1, this is still going to be positive. So you notice that everything is going to be positive in this second case. The third case is when x is less than -1. So let's say it's -100, okay? Now what you do in order to make sure that's taken care of is to fix this. So just look at this. If I rewrite this as x to the 4th plus 1 plus 4x squared plus x, and x is negative, -100. I know this part is going to be positive because any negative number to the 4th power is positive, plus 1 is still positive. When I go here, this is a negative number, -100. Just plugging in the number so you can see. But this is the square of a negative number. The square of a negative number is going to be a big positive number. It's going to be square of 100 is 10,000, but it's going to be positive. So times 4, by the time you add it to the big negative number, it's going to end up being positive. So no matter what you do, this will always be positive. And because it will always be positive, it cannot be 0. And because it cannot be 0, it does not contain any real roots, because real roots must exist when the function crosses the x-axis. This does not cross the x-axis and therefore does not contain any real roots. Remember, this is supposed to have 4 roots. So out of the 8 potential roots, we have eliminated 4 of them just by showing this. Therefore, we're counting on getting 4 roots from here. Some of them may be real, some of them may be complex roots, but we don't know yet. We still have to investigate the second polynomial. So for now, I'm going to erase this and say that this one has no real roots. Now we're left with just this polynomial, and we're going to try to find the number of real roots that it has. You have 2 options. Solve this, or just find the number of real roots. And let me tell you, don't try to solve it unless you really know what to do, because the way I'm looking at it, it doesn't look promising at all because of this 4 here. So what you could do is go back to your pre-calculus days and say, I learned in pre-calculus that all quartic polynomials will always have both hands raised up. Remember, so you don't need to think about this. That's what a quartic polynomial always looks like. Now, whether the middle twists badly or positively, or whether the middle, maybe it's just like this, it doesn't matter. Or it's just flat. It doesn't matter. But all quartic polynomials with a leading coefficient that is positive will always have both hands raised up, just as you would have in the case of a quadratic. So as long as the power here, the degree of the polynomial is even, it will always have both hands up. So it means as this approaches infinity, as x approaches infinity, the polynomial approaches infinity. So you're going positive, coming from positive, you're also going to positive. So the only way you want to know the number of roots that are real is how many times this polynomial crosses the x-axis. If you can decide that, then you know the number of real roots that it has. Okay, so how do you know that? Firstly, if you don't understand this, just take the limit. If you take the limit as x goes to infinity, you're going to see that it's going to be positive infinity. Take the limit as x goes to negative infinity, it's still going to be positive infinity. Okay, let me just do one for infinity. The limit as x goes to infinity of q of x is going to be the limit as x goes to infinity of, you see this expression? Anytime you're doing for polynomial, just factor out the biggest degree in it, okay? Factor out the biggest part of it. What's the biggest part of it? It's x to the 4th. So it's x to the 4th times 1 minus 4 over x squared minus 1 over x cubed plus 1 over x to the 4th. So you notice that as x goes to infinity, this goes to 0, 0, 0. So what you have is just x to the 4th times 1. But x to the 4th is infinity to the 4th, which is positive infinity. If we had changed this to negative infinity, let's say it's negative infinity, it will still be the same thing, but negative infinity to the 4th is still positive infinity. So you see, both cases, hands up. Okay, now, what do we need? One thing you want to look at is, look at the polynomial. It is very clear that when x is equal to 0, if you plug in 0 everywhere here, you're going to get 1. So we can say that the value of the polynomial when x equals 0 is equal to 1. Okay, so this is the picture that I have just painted. I have painted a case where it is positive before, as you come from negative infinity, and then it's positive as you go to positive infinity. And at some point 0, look here. So it means at some point 0, the polynomial has a value of 1. Here, it goes to infinity. Here, it goes to infinity. You just need to show that when this polynomial makes this curve, it actually touches or crosses. Because if it crosses, it must do so at 2 points. And if it does the same thing on this side, it must do so at 2 points. Then you have 4 real solutions. Otherwise, you're going to get maybe 2 or you're going to get none. It's not possible to have none. Well, I don't know. Let's try it. So what we're going to do is, since we have plugged in 0 and we got 1, which is a positive number, we want to see what's going to happen if we plug in a number just before 1. So the good number, but just before 0. So let's plug in -1. So we're going to go here and say q of -1. What does it do? That my board is getting rough. Too many explanations. What's going to happen if we plug in -1 into this polynomial? This is going to be 1 minus 4. 1 minus 4. Let's plug in -1 here. It's going to be +1 plus 1. Ooh. Did you see that? We're going to get -1. So we're getting a negative value just to the left of 0, which means here, something happened here. So this actually goes this way and then comes back up. So guaranteed, okay, that there is a real root here and there is another real root here. Well, you know, any theorem you want to use it. What's the theorem we're going to use here? The intermediate value theorem, right? The intermediate value theorem we're going to use here. So there must have been a point where it is equal to 0. And you go this way also. Remember, all of what we're doing is trying to find the number of real roots so we know what n is. Okay? So we already know we're going to get R1 plus R2. But we need to know what's going to happen here. You do the same thing. Plug in 1 now instead of -1. If we plug in 1 instead of -1, what's going to happen? We're going to have 1 minus 1 minus 1 minus 4 minus 1. So it's going to be 1 minus 4 minus 1 plus 1. That's still going to be 1 minus 4, -3. So you see that we get another negative just to the right of 0, which means there's another negative here. Okay, so it means we have this using the intermediate value theorem. So we can guarantee that this polynomial will give us 4 real roots. So our n for this problem is 4. And this is the polynomial we're going to use for, what's the guy's name again? Vieta's formula. Okay, let's do some cleaning up. There is a trap in this problem because there's a tendency for you to think that this is the polynomial that Vieta talked about. But this is not the polynomial. The polynomial Vieta talked about must have every single term. This one is missing the x cubed term. So we have to rewrite this actually. This is the same thing as x to the 4th plus 0x cubed plus, sorry, not plus, minus 4x squared minus x plus 1. This is the actual term we're going to use. So now, if we want to find the sum of the real roots, which are the sum of the roots of this polynomial, which are 4, and they're all real, we know that R1 plus R2 plus R3 plus R4 is going to be equal to, by the formula, it's going to be minus a sub n minus 1 over a sub n. A sub n is the leading coefficient. A sub n minus 1 is the next one, which in this case is 0. So clearly you can see that we're getting 0 here. This is going to be negative 0 over 1, which is 0. But this is not what the question wants us to find. We're looking for the sum of the squares of the real roots. So what we're going to do now is try to find r1 squared plus r2 squared. And the shortcut to that is to square the sum. Okay, so we're going to have r1 plus r2 plus r3 plus r4, and then we're going to square it. If we square this, now I want you to do that yourself. This is what you're going to get. You're going to get r1 squared plus r2 squared plus r3 squared plus r4 squared plus 2 times all the products, the pairs, r1 times r2, r1 times r2, r1 times r3, r1 times r4, and then r2. So you're going to have, that's what you're going to get. And by Vieta's formula, we know what this one is. It is the next term, okay? So this formula is given as, we already found this to be 0 squared. This is the guy we're looking for. It's going to be plus 2 times, now there's a formula for this, which is basically just as we had a formula for this one. The formula for this is, no more space, is plus minus plus. So here it's going to be a sub n minus 2 over a sub n, and we don't need to put a minus sign on top of it. Okay, so here what do we have? This is the term, negative 4. So this is going to be equal to minus 4 over 1, which is minus 4. So this is minus 4. Okay, so we have 0 squared equals something times minus 4. Let's write it as the sum. We know that r1 squared plus r2 squared plus r3 squared plus r4 squared is equal to, because if this sum of all the squares is added to a negative 8, this is going to be just 8. When you move it over here. Yes, that's the answer. Never stop learning. Those who stop learning, stop living. Bye-bye.